Okay, so we still have a little bit left to finish notes 50. I just broke it up yesterday because it just seemed like it was long enough. That was long enough for notes. And this little bit will kind of be like a good refresher anyways. So it says, note that both types of reactions require a certain amount of activation energy. So in both of our charts yesterday, we'll just scroll up for a second, maybe we'll let me see our charts, our exothermic and our endothermic charts. Both of them required this activation energy, meaning that you could not get that reaction to start without having at least that much energy to get you to your activated complex will actually make the reaction start happening, okay? So they each take a certain amount of activation energy, but if you notice, exothermic, which gives off heat, it doesn't need as much to start. So it doesn't take as much energy to start, but it gives off a lot of energy. So this is the energy that's given off, that difference from reactants to products, where it's backwards in endothermic. So endothermic takes in a lot of energy, so it makes things feel cold, but it's taking in energy, absorbing energy. So it needs a lot of activation energy and doesn't give off as much. So like this change from reactants to products is not giving off as much as the exothermics, but they still both require activation energy to begin. All things require some form of energy input or that reaction is not going to occur. Now that energy could be through adding a catalyst, that energy could be through adding heat, adding stirring, like anything that's going to get those particles to collide more. So remember yesterday, the collision theory, anything I can do that will get them to collide more will give me the energy I need. All right, so the amount of energy needed to begin a chemical reaction, that activation energy for an endothermic reaction is considerably larger than the activation energy for an exothermic. So that's what we just said by looking at the chart. So the activated complex, remember the activated complex is the top of the hump, okay? So the activated complex is the transition state consisting of unstable intermediate forms of atoms, molecules involved in a chemical reaction. So basically it's like I have to have all this energy to get to this tipping point when the reactions are starting to be unstable enough that they'll actually swap partners. They'll actually make a new compound at that point. Because you've given them so much energy that they're actually they'll consider to become unstable for a second and swap partners. And that's that activated complex at the top. The enthalpy of a reaction, which is kind of what this whole note set is about, the enthalpy of a reaction, or the heat of the reaction, is also written as triangle H reaction, which means change, or in the triangle in math means change, so change of heat. That's what enthalpy is. It's the energy change. It's the heat change from reactants to products involved in a chemical reaction. Note that the heat of a reaction will be negative for an exothermic reaction, so it's always negative if it's exothermic because I start with a lot of energy, but I lose a lot. So see this loss? I went down in energy. This is where I started. This is where I'm ending. So since I have less energy that I do at the end than I do at the beginning, that's a negative reaction. So that's exothermic, and it's always negative. Whereas, and then heat is given off, so it feels hot. Whereas in positive reaction, so it's always positive for endothermic because the heat is being absorbed. So it starts down here, absorbs a lot of energy, and doesn't give off as much. That isn't a very good representation. Let's put it up here. So I'm starting here and ending here. So I actually had more energy at the end of the reaction than the products did. Than the reactants did at the beginning. So this is a positive reaction, and endothermic reactions are always positive. Okay, so that's just a little recap of what all those terms mean and how they look different between an endothermic and exothermic reaction. Now, there's another way we can look at the heat of a reaction. You can actually have that heat of the reaction, or the enthalpy of a reaction, that change in energy, you can put it in a chemical equation. So here's our chemical equations. We've learned how to balance, we've learned how to write, we've talked about neutralizing them in our last unit. So lots of reasons for having these chemical reactions. You can also add in the heat change. They don't always add in the heat change, but they can. You can add that into the reaction to show what the heat change is. And where you put that heat change, so it's always in kilojoules, all of our energy change is in kilojoules, where you put it either on the reactant side or the product side. So let's put it over here. This is the reactant side, remember, from the arrow. And then this is the product side. If it's on the product side, that means the energy is being given off, okay? So it's on the product side, so energy is being given off right now. what type of reaction had the energy being given off? You're actually feeling that heat. That was an exothermic. So if the kilojoules, the energy is on the product side, meaning it's being given off, then that's an exothermic reaction. A chemical reaction in which the heat is given off or released, the heat term is on the right side or on the product side. I'm going to say the product side to be more particular. So it's on the product side of the equation. Okay, and then vice versa. Over here, I have the kilojoules on the reactant side. So it's on, it says left side. I'm going to change that. Let me put reactant down here. That's more clear. It's on the reactant side or the left side, and that's an endothermic reaction. Endothermic reaction are always going to have those energy on the on the left side, on the reactant side, because heat is being absorbed. I have to absorb a lot of energy for that reaction to take place. Just like our chart showed up here, the endothermic, remember, it has all that energy it has to gain, whereas the exothermic only has to get a tiny bit and gives off, so it has a way bigger dip, so it's giving off a lot more energy. And you can see that represented in the chemical equation. Okay, just a little bit left. It's just like a little practice, basically. Okay, let's do this little practice. So it says these types of equations are called thermoequations. Equations that include the amount of heat that is released or absorbed. This line isn't supposed to be there. So that was supposed to be taken out, and I forgot to erase it. So it's not there. But those are called thermochemical equations, the one I just talked about above, that have the kilojoules on either the reactant side or the product side. They're called thermochemical equations. All right, now let's do a little practice. So we have this diagram off the side, right? Okay, it's just like the other one. If you notice, it's needing so this is my reactant side, this is my product side. I'm ending up with more energy at the end. So remember, when I'm ending up with more energy at the end, I'm having to absorb a lot. So like right here, from here to here, from where I start to where I have to get to the hump, remember that's my EA, my activation energy. So my activation energy is that one. As it was labeled in your practice charts yesterday, it was called EA, your activation energy. I don't know why I put E before it, but that's your activation energy there. So over here, I already know this question. It says this reaction is endothermic or exothermic. Well, this is absorbing a lot more energy than it's giving off. So that's an endothermic. It looks like our endothermic charts from yesterday. Now to the actual question. So it says the activation energy of the reaction is about what? So I just said that. So the activation energy is from where I start to where I have to get to. Well, I just have to do some math. So I start at 80 and I end at 240. It's where I have to get to. So I'm going to go from, I have to get to 240. High speed so swiftly. I'm going to subtract off 80, and that will be my answer. So 240, 740, 60. And notice it's positive. It's positive because it went up, right? So anytime you're going up, I have to gain 60 kilojoules, or this reaction is not going to occur. Okay. Now it says the heat of the reaction, or triangle means change. The change in heat, which is also enthalpy. They could have put any of those. They could have said, what's the enthalpy of the reaction? They could have said, well, what's the heat of the reaction? They could have said they could have just not even put that sentence in there, just said the triangle H, which means change of heat. Any of those ways they wrote it would have been correct. So enthalpy, now it's all messed up. Enthalpy, triangle H means change of heat, heat of a reaction, all means the same thing. It means from where I started to where I ended. So this little block right here, from reactants to products, where I began and the energy I had at the end, what is that change in heat? So the change of where I began, the change to where I ended up. So for one, I went from a lower number to a higher number, so I'm going up. So this is a positive change. This is the one that you actually have to give me a positive or negative. And this time I am gaining energy in this reaction. That's why it's endothermic. And I'm going from an 80 to a 160. So I'm going to go 160 minus 80. So take off the 60, so 60, then 20, so it's 8. Okay? So it's a positive 80 kilojoules of change. That's going over here. So positive 80 kilojoules. And there we go. So just another little practice over it, because you're going to have some of those practices today on your worksheet. Okay, so notes are completed. So I'll finish erasing that after I pause it.